So I am back to the slides for the last class. And we have studied Markov chain Monte Carlo. At that time, it was for the case of a discrete distribution. And the case was this. We have a certain probability distribution for 3 states, and the values of the distribution, the probabilities are these, 0.2, 0.6, 0.1. And we know that these values should sum up to unity. And we'd like to make samples that satisfies this distribution. And the answer was either of these 2 matrices. One is from Metropolis algorithm. The other is a Metropolis-Hastings algorithm. And whatever matrix we use, we get the answer. And in view of the Markov process, the thing is that we'd like to find out what kind of a transition matrix here T will give us the solutions, the samples. That was the problem. And using either of these algorithms, we could find out the matrix, transition matrix. And once we have this matrix, we can iterate. We can draw a single sample at each step. And by accumulating those samples as we continue the iteration, in the end, we will get a large number of samples, and those samples will satisfy that distribution. Now we move to the continuous version of this process. And I already, there is also the Metropolis-Hastings algorithm in case of discrete distribution. This applies also to the continuous version. The most popular method is the Metropolis-Hastings. And in this algorithm, we'd like to get samples satisfying a certain probability distribution, which is given by Px in this case. And within this algorithm, we need to introduce an arbitrary proposal distribution. I call this as Q here. And for this distribution, we have to have the ability that can make samples easily from this distribution. And the step is to sample a new point x star based on this proposal distribution, given the current point x. Then we calculate a certain ratio, which is given by this equation. And based on this ratio, the value of this ratio ranges between 0 and 1. And based on this value, we decide whether to accept a new point or not. If this value is high enough, we accept that new point and add to the existing sample. Otherwise, we stay at the old point, the existing point. And this can be stated that the continuous counterpart of the transition matrix that I mentioned before. And this process is also explained in this box. We start at a certain arbitrary single point, here x0. And then we sample a new x using the proposal distribution, here x star. And calculate the ratio like this. And the ratio ranges between 0 and 1. And if this value is high enough, we accept the new points. Otherwise, we go back to the existing point and repeat this. And by this way, we add more and more samples. And in the end, a large number of samples will be obtained. And that will represent the target distribution, Px. So I think that the algorithm itself is not that difficult. Only based on this, everybody, if one has a little ability to make codes in a Matlab, they can implement this easily. Within this Metropolis hastings, Metropolis algorithm is a little simpler version in which the proposal distribution is symmetric with respect to new points and old points. Remember that we have to, this distribution has to have the ability to make samples from that distribution. And based on a certain existing points, a new point can be sampled. A good example for this symmetricity is the normal distribution. When we use the normal distribution, it is symmetric with respect to the 2 points. When we use the normal distribution, the notation here represents, we have a distribution with the mean at x, mean at the existing point. And we sample randomly a new point, x star, based on this distribution, which may be somewhere like this. And the value of this, the distribution value of this is this height. So this is the value of Q here. And the symmetricity means we reverse this. In this case, we have the mean at x star here. And the same probability distribution can be constructed like this. Then we'd like to calculate x in this distribution, which is the height here. This is the Q at the right side. This is the Q at the left side. We can see these two are the same. In this case, we say the distribution is symmetric. So if the proposal distribution is symmetric, we can remove within this expression. And it's further simplified. The ratio between new points, the probability distribution of new points and old points. Based on this ratio, we iterate, like I said before. We we take the new points or not. Another interpretation of this ratio can be explained like this. Although this is a kind of a transition probability within the Markov process, this can also be explained as if the probability value of new points x star is higher than the old points, it is highly likely that we can take that new point as a sample. This is another interpretation for this. And if it's greater than 1, always take that. Because we have this ratio ranges between 0 and 1. And if it's greater than 1, it is also the same as the 1 unit value. And we compare this with the randomly generated how do I say, in Matlab, a simple random generation number varying between 0 and 1, and compare this value with the normal randomly generated value. And if this is greater than this one, we take that. If this is small, we don't take that. That means the new point, regarding the new point, if the p-value compared to the old value, old x is small, it is not likely that we take that sample. Yes?
If we take the normal distribution here, then maybe 70–80% of the time we will accept the point. Because first of all, we have 50% chance that P of X star will be larger than P of X. If we make the mean X and sample it, we have 50% chance of being on the left, 50% chance of being on the right. So 50% of the time we are sure to accept it. And in the other cases, we still have a substantial chance of accepting it because P of X star over P of X will normally be close to 1. So that means that maybe 70–80% of the time we will just accept it. Doesn't that slow up the sampling?
Let me explain and answer to the question using this specific example, and let's look at what happens. So I will show you this algorithm using the example problem, and this problem was addressed before for the in the last class when I explained about the simulation algorithms. I hope you remember I told about the rejection sampling, impedance sampling, things like that. I use this example problem. So the same problem is used to illustrate this algorithm. We'd like to sample, we'd like to make samples, obtain the sample, large number of samples that satisfies this distribution. And this distribution is a little strange looking distribution. Have two peaks in the two different places. And for this, I introduce an arbitrary. The reason that I say arbitrary, we can use also the other type of distribution, not only this one. In this case, I introduce the normal distribution with the mean at an existing point x, and the standard deviation always 10. And for this, I have to implement the Matlab. So I define the target distribution. And at first, look at the shape of this distribution, because I can calculate the distributional value at any point, and it looks like this. And the point from now is we'd like to make samples, not just drawing this. We'd like to make samples that satisfies this distribution. And it should be something like we have more samples here than here. We should not have many samples around this region. If that's the case, that's something wrong. So very small samples, no samples here, and the large samples, we have to expect that as a result of this process. And this is the iteration. I use number of iteration here because I skipped here. In this case, I used the number of iteration or the same thing, number of samples or number of iterations, whatever, is the 10,000. So we will expect that we get a 10,000 number of samples by iterating through this algorithm. And yes?
I'm sorry, but in this case, we have some cases that rejected our iterations. So in that case, the number of samples is not equal to 10 to the
Yes?
4, right?
Yeah, it was the case of a rejection sampling. Your question is, in your process, is it do we have the less number of samples as a result of the iteration? Because sometimes we reject the sample.
Yes.
That is not the case. In this process, even if we do not take the new sample, we take that existing sample within our group. Yeah. So this process, I will just explain conceptually. I would like to make samples for this. And I start with the point 0. And I remember it was -5 was located here, and it was +10. So 0 will be somewhere around here. I start at this point. And I sample a new point based on the normal distribution. Normal distribution with the standard deviation 10. You can imagine whatever kind of a point can be taken by drawing a single point, single sample that satisfies this distribution. This is the mean. You can, there is a many chance to have a certain point, but very rare chance if we go farther from this point to the left or right. But around here we have a greater chance to any point, take any point. It doesn't have to be like that. Your question is, should we have the proposal distribution such that it covers the entire region? No, you don't have to do that. We just, at a certain point, the purpose of this proposal distribution is we'd like to move around this existing point. So we would like to move around. When I say around, means we around here, not here. And this normal distribution explains that. So let's say we obtained this new point because it is random, and we compute new p x star, this because it is new points. And this is old points, px. Compare this one and this one. You will see in this blackboard. And what we compute is the ratio between the height of new p and old p. If this is high enough, we absolutely take it as a new sample. Otherwise, we stay at here and try one more time, simulating. Next time, we will get still the same point, but more likely the other point comes in. And compare this and this. If it's satisfies the criterion, we take that. Otherwise, still stay at this point. This is the idea. So with this, I hope I could have explained the answer to your question.
Yeah, I made a mistake. The ratio is of p's. I calculated it as if the ratio was of q's.
Yes. And the rest of the procedure, I don't have to do that because already you will make the results. I gave you already this code and you will do by copying and pasting. It's a very simple thing. And the results will be something like this. The first figure at the bottom represents the so-called trace plot of the variable x. The horizontal axis represents the iteration. I told you we have a 10,000 iterations, so 0 to 10,000 it is. The vertical axis, just x. We have a bunch of x moving around here. So this means the above this range, below this range, we have no chance to take samples. And only within this region we have many samples during the iteration. And as a result of this, we have obtained 10,000 number of samples. We can draw histogram using the samples, which is this. We have a large number of samples around here and less or no samples beyond and above this range. And compare this with the shape of the PDF, you will see the exact agreement. Yes?
So I think the important thing is to choose the standard deviation of profile distribution.
Yeah, your question is the standard deviation of this is quite maybe important.
Yeah, so
I will explain. Yes.
I have the same question.
Yes. Great point. And the last figure represents the cumulative distributive function of the two, one from the histogram, the other from the exact shape, exact expression. And you will see the close agreement between the two. I have some notes with this process. First one is very obvious, no doubt. If we have only a small number of samples, that is not likely the true solution. So at the early stage, the histogram will be very bad. And only if you have a sufficient number of samples, you will get the solution. Second, the same thing. In the same manner, the early stage samples, because it is bad, it is not recommended to include them in the samples that we want. We have to discard some part of the early iteration until we get sufficient convergence. I hope you remember land of odds problem. At first, you saw little states, and soon you found it was converging to a certain state. Same thing. In the early stage, it is not converged yet. And from this point on, we get converged states. And from this point, every sample satisfies the target distribution. How early and how long do we have to discard? I don't know. It depends on the characteristic of the problem. That's the problem. That's the difficulty in this process. So we have to always check this kind of trace plot, the process using this trace plot. This is the result of the when I started from 80 instead of 0. The previous example, previous result that I showed was starting from 0, and in this case, I started from 80. So very far from this region. And the process tries to find out where is my range, where is my effective range. The early stage is the results of that.
I'm sorry, what is that plot showing that you're just, like, what are the axes on that plot?
The axis, the horizontal axis of this figure is the iteration number. So early stage of the iteration, it did not get the correct point yet. And after a number of trials and error, fortunately, he got the region. And once we reach the region, we stay within that effective range. And the samples always within this region.
So the trace plots, why is the trace plots from x equal to 10?
In this figure, this I call the trace plot of the x. So the vertical axis represents the value of x, and the horizontal axis represents the iteration.
The other one is not the same trace plot?
This is the one that I showed you before, and this is the nice results in which I started from x equal 10. Yes. In the previous slide, previous slide started from x equal 0, and this is results when I started from x equal 10. This is from 80. So 0 or 10, it gives us a very good results even from the early stage. But when we start from the point very far from this region, which is 80, it's problem. We have a trial and error to find out the good point.
So you don't want the case where at some iteration value you just start getting pretty constant x values? Is that what you're trying to avoid?
Your question is regarding this figure,
Yeah.
and what is your?
I'm asking what behavior in that figure are you trying to avoid?
The behavior that I'm trying to avoid is to, I'm not trying to avoid something. I would like to explain that if we choose the starting point, in practice, in reality, we don't know what point we should start. So we start with an arbitrary point. And unfortunately, it turned out to be far from this region. We have to have some process to find out that region. This is that region.
So because it flatlines, or roughly flatlines at the back?
The scale is different. You can compare this figure with this figure. If we remove this and scale down this, we will get this one. Yes.
If we know P of x, shouldn't we know what region we want to be in? Where to start?
That will be much better to get the solution. If we have any idea that the location or region is where, we can start from there. You don't have to start from the point far from there. Next. Already some students asked me how you choose or impose some values for the proposal distribution. That is another trouble, another difficulty in this process. It requires, how do I say? this is not a scientific decision. Based on experience, you have to gain some knowledge about this. This is the 3 different results when I employed the different standard deviation. This was the one that I showed you before. And this is the nicest result, the best result. And let's say we take another value for this, while the others are the same. We change only the standard deviation from this to this, very small. We get not good results. The reason is we move around from the proposal distribution. Remember this. If the standard deviation is very small, we start from here. There is a high chance that the points stay within this region because the standard deviation is very small. We have a very rare chance to get the point far from here. But nevertheless, sometime in the future, we get these points because there is still a chance, although it's very small, to get this point. Once we get that point, we stay for a while at that region. This represents that result. We started somewhere in here and stayed here, and somehow we could move farther from here to here. But still we have a small standard deviation. We could not avoid this one. We had to stay within this region. This is the result. The opposite end is this, when we employ very large standard deviation. In that case, we move too far every iteration. So from here to here, from here to here, we have a less chance to move near that point. Always greater movement. That is another bad point in this process. The same thing, but another problem I introduce here to emphasize the importance of number of samples. In this case, the target distribution is very easy, uniform distribution. And employing MCMC is very stupid. We already know how to make samples for this. But even though this is the fact, let's try Markov chain Monte Carlo for this distribution, assuming we don't know how to make samples. And with the 10,000 numbers, we still don't get the convergence. And after having more number of samples, although still poor, you will see it is converging to the uniform distribution. So another one that I have to mention here is I always introduced you about the Metropolis algorithm only. In case of Metropolis Hastings, remember, we have a more complex ratio. There was P and Q, also the nominator P and Q. We saw this kind of expression in the Metropolis Hastings. In the Metropolis only, we removed this. And in case of Metropolis Hastings, that means we employ the asymmetric jump. When I say jump, it means I move around. I sample a single sample based on the proposal distribution. In this terminology, in this Bayesian textbook, they say this as jump. So a symmetric jump represents, we employ the Metropolis hastings. Symmetric jump, that means we use Metropolis only. I did not practice myself in case of Metropolis hastings. And if anybody is interested, you will employ the asymmetric, another kind of proposal distribution for this purpose. And the textbook states that if we employ the asymmetric proposal distribution, it will speed up the convergence of the iteration. There is also a Matlab function for this. That means we don't have to code ourselves. Already, Matlab has it. So you just use it. And I also included that in the Matlab code. You will find it. Very easy. And in order to do this function, you need provide information for this. You need to provide information for P, which is target distribution. You also have to provide Q, which is a proposal distribution. And also you have to provide the how to generate random sample from Q. That should be included in this function. And there are many variations of this algorithm. At least I saw more than 20 algorithms as a variations, and I don't do this in detail here. Yes?
Going back to Metropolis algorithm, if the only way to check whether we have chosen the correct standard deviation for Q is by looking at the trace?
Yes.
That is the only way to
Yeah.
whether we
Whether I get a good result, good distribution, is just look at the trace plot. Here is another interesting method. From this time, I move to the optimization problem. And the part of the students are from the optimization lab, and the people can be interested in this. There was an algorithm named simulated annealing back in 90s and 2000s. These have gained much popularity at the time, and they're still popular. This gives us the global optimization, optimum point solution for a function. In this case, let's consider the probability distribution Px. We think this as an objective function. In that case, what we want to know is the point at which the p-value is highest. And using the Markov chain Monte Carlo, you already found it. By iteratively sampling and drawing histogram, if you find the point with the highest value, that gives you the solution. But the simulated annealing, the idea of this is much more than that. It accelerates. It accelerates the Markov chain Monte Carlo process by introducing this value. By putting this value on P, as the iteration continues, the high value of P gets more higher. The low value of P gets much lower. And gradually, this trend increases. I'll show you the results. this is the result of the traditional Metropolis algorithm. I already explained this and already showed the results. This is the result of the simulated annealing. In that case, in the end, we get the accelerated results, which means that with lower value, we'll get much lower. Higher value will get much higher. So results of that, we get this, the figure like this. And we see here, this is the optimum solution point. And the only thing that I did from here to here is by adding this one. That was it. And the other is the same thing. And this is the idea of simulated annealing. Now we move to the Gibbs sampler. Gibbs sampler is nothing but about the multi-dimensional problem, because the problem that I explained to you before is always about single variable. But in practice, we have many cases for multiple variables. This is for that. And we also call this as alternating conditional sampling. The concept is very easy. Explanation is very difficult. That's my problem. So if I use this statement, it is not easy to explain. So I just show you a simple example. We have 3 parameters, not just one. So x1, 2, 3. We'd like to make samples for these 3 parameters. At the current iteration, we have 3 different values, x1, x2, x3. And it is at the I-1th iteration. And at the current iteration, which is I, first I draw x1 conditional on the given x2 and x3 previous. And we write this like this. Hope you are familiar with this expression. The probability of x1 conditional on the others. So the conditional on the others, in that case, these 2 come from the I-1th iteration. Next, for the x2, in this case, we draw sample conditional on the current x1. Just a moment ago, we made a new sample that is turned into the given value right away. And still the x3 comes from the previous I-1th iteration. Third, x3. We'd like to make x3 based on the others. In this case, we already made new samples x1 and x2 at the current iteration. We use those 2 as a given value. This is the idea. And this is the generalized statement for that. Yes?
What's the advantage of using that type of sample?
What's the energy?
Yeah, like what?
Advantage of a Gibbs sampling. If we have the method only for the single variable, if we have a method to make samples only for the single variable, we have to use this one. Because each one of these gives us the solution for single variable. So if you can handle the multiple variables at once, we don't need the Gibbs sampler. And I will explain also about that. This is the example. In order to illustrate the Gibbs sampler, the Gelman's textbook used this example. And you have to understand what is multivariate distribution, or in case of two parameters, bivariate normal distribution. We always study using the single variable. And if we have one more variable, we assume that those two are independent each other. So we can sample independently for 1 and 1. But if those two are correlated with each other, that is not the case. In that case, we call it bivariate normal distribution. And the distribution is stated in this way. Although this is still the same character n, in this case, n is no longer just simple normal. In this case, n represents multivariate, bivariate normal distribution. And the mean is at y1 and y2. And their correlation or covariance, whatever, the matrix, in that case, this part is given in the form of matrix. This is the standard deviation. These two, the symmetricity, so only one is needed, represent the correlation of the two parameters. And in this example, we introduce these values and make the solution for this, which means that we make the samples that satisfies this bivariate normal distribution. In this case, I put correlation coefficient rho at 0.8. 0.8 means a strong correlation between the two parameters. If y1 gets higher, y2 is also likely to be higher. If y1 is small, y2 is also likely to be small. 0.8 represents that kind of a feature. And as a result of the sampling, we got this point distribution. And we could see there is a strong correlation between the two parameters. And this result was obtained by using Gibbs method, by alternating sampling x1 based on x2, and then x2 based on x1, back and forth, and repeating. And we got that result. The thing is that for this specific example, we have to have the information or knowledge how to make the conditional distribution. We have to derive mathematically for that. And the result is these two expressions. And using this, we can sample conditional on the other, the 1. So the point is Gibbs sampling is not the kind of a Metropolis or Metropolis Hastings. It doesn't have anything to do with the Metropolis or MCMC. Gibbs sampling is only about the method for multidimensional problem. So once you have the alternating scheme, the sampling can be made by whatever way. If you have any good Matlab function, you just use it. If you don't have it, you have to use the something like Metropolis algorithm. So in this way, Gibbs sampler should be understood. In that context, I already introduced the two results in the Matlab code. One is the Gibbs sampling using the Matlab command, normrand, normal distribution random generation. And in the other part of the Matlab code, I also used the Metropolis algorithm for sampling this. So Gibbs sampling can be combined with the Metropolis algorithm for the multidimensional problems. The last thing is, I told you, one student asked me whether we can make samples simultaneously or not. Gibbs sampler only allows me the when I can have a single parameter sampling. But in this case, we can also do the same thing using the multi-parameter sampling. And because the class is finished, this is the almost the end of this MCMC algorithm. But I have to continue explanation day after tomorrow. Yes, and I also have the recitation this 3 p.m.